Hello everybody, it's Percy here. Today I want to talk to you about binomial probability distributions. So, at the heart of it, binomial probability distributions lie over this guy. What is this guy? It's a Bernoulli. Okay? So we have Bernoulli trials. And the thing with these Bernoulli trials is that they are binary in their outcome. So they get assigned a value of 1 if it's successful, and they get assigned a value of 0 if they're failing. All right? So the classic example is a coin toss, right? You have a coin toss. If it lands heads, we can define it as 1, and if it lands tails, we can define it as 0. It doesn't really matter. It's just we define heads as success. So this is really important for reasons that we're gonna cover. Suppose we have, we toss a coin 7 times, right? And just for fun, we're gonna make this an unfair coin, which just basically means that the probability of heads and tails are not 50-50. It's a biased, whatever you want to call it. So we have 7 coin tosses, and just suppose that we would like to know the probability of getting, let's say 3, right? We want to know the probability of getting exactly, and this is important, exactly 3 heads. And just let's say we rig the coin, and the probability of the coin landing heads is P1 equals 69%. Because why not? Right? So, yeah, we have 7 coin tosses. The probability of landing the heads is 69%. What is the probability of us getting exactly 3 heads? Let's just say we have 7 coin tosses, so we got 7 spots, right? 2, 3, 4, 5, 6, 7, right? So we have 7 consecutive coin tosses, and each one of these guys can either be head or tail, right? Head, tail, and so on, right? So essentially, we can deduce this. 2 outcomes in here for 7 times 2 to the power of 7, right? 2. And so we have 2 to the power of 7 potential outcomes, right? Like potential sequences. Right? 2 to the power of 7 potential sequences of how this thing can turn out, right? And the thing is that we know if we're given this probability of success 69%, the probability of failure is 30 plus 1 as 31%. Okay, mathematics. So how the fuck can we calculate the probability of landing exactly 3 heads? That's what we're going to do next. So we just calculated that we have 128 possible sequences, right? So it doesn't matter about like the 3 heads, right? So from 0 heads to 7 heads, we have 128 possible sequences of right? Okay. All right, check it out. So we just calculated the possible number of sequences to be 128. Now, we want to know the probability, the cumulative probability of 3 heads and 4 tails, right? And the thing is that reordering these guys, right? We don't, this is a valid sequence, I don't know, heads, tails, and okay, this is also a valid sequence. So we have a bunch of sequences that all result in us getting exactly 3 heads, right? One thing that you can do is to brute force it. What do I mean? Is that you can either, okay, you can write every single possible sequence with 3 heads inside of them, right? And what is the probability of a given guy, right? The probability of us landing 3 heads in one sequence, right? So let's just get a given sequence, heads, tails, that's probability of a 1 powered cube times probability of tails, or a 0, 4. All right, but, yeah, you know what I'm trying to say. And so why is that? Because heads, 0.69, heads, 0.69, heads, 0.69, P1 cube, tails, 0.31, tails 0.31, tails 0.31, tails 0.31. And no matter how many different sequences that you have with different, different placements of heads and tails, all of them share this probability, right? Because the only thing that changes the probability is how many heads versus how many tails you're computing for, right? So if I were to brute force this problem, right, we can factor out all these this guy, because all these sequences with 3 heads have this probability. So if only I knew, if only we knew the possible number of sequences with 3 heads, all of them, we could just have like number of unique sequences times, let's say, I don't know, P, we just call it PF for fun, so we don't have to write both of these explicitly, right? Number of sequences times probability of F, which is the probability of this event, right? We could basically calculate it, right? Because this has a probability and that one has the same probability. So for every single one, the probabilities kind of stack, like Magi's Soul Stealer, if you play League of Legends. So now the problem becomes, how the fuck do we get every possible sequence with 3 heads and 4 tails? We could brute force it for sure, but we don't have all day. So we came up with something very, very clever to count the number of sequences with exactly 3 heads and 4 tails. Basically, our job is now to find the proper sequences or permutations with these specific heads and tails values, okay? How the fuck can we do that? Well, we do kind of a trickery, right? So what is the possible permutations of this guy, right, if they were unique? And what do I mean, right? And look. So what we're gonna do is that we're gonna treat all these guys as distinct fuckers, right? We go head 1, head 2, head 3, tail 1, tail 2, tail 3, and tail 4. And we basically know that if all of these guys are unique motherfuckers, right? The total number of permutations for these guys would be 7, 6, and so on, equal 7 factorial, right? But the thing is that this is, if we have unique heads and we have unique tails, then we get 7 factorial. But the thing is, they're not unique, right? We're kind of counting them multiple times. What do I mean? It means that although we have the 7 factorial from this, we overcounted because h1, h2, h3 is the same as h2, h1, h3, right? All the ways that we can, permutate these 3 heads and these 3 tails, they don't really matter. All we want is the permutations of heads and tails themselves, right? So what we essentially do is we discount it. Why? Because look at this mini set within this set, right? All the different possible permutations for this h1, h2, h3, well, these are just 3 factorials. And what does it mean? It means that we did use this factory, this trickery, to calculate this. But this guy has 6 versions, right? 3 factorial versions because of the permutations within this set. So we just discount it, essentially. And it's the same idea with these guys, right? These guys, for every valid sequence that has 3 heads and 4 tails, doing 7 factorial counts these guys 4 factorials, right? The different permutations. So essentially what we are doing is that we're treating them as unique, get all the sequences, and then we're just taking out the permutations caused by these guys and the permutation caused by these guys out of it. So that's why you get this thing, okay? 7 factorial, 3 factorial, 4 factorial. We're just, we fucky, it got sucky, so we're just unfucking this. We're unfucking this 7 factorial. And if we were to generalize this, we could write this as n factorial, r factorial, n minus r factorial, right? But this thing in here, this looks very similar to another fucker, but it's different. Although this exact same formula has a different logic. What do I mean? A quick side tangent so we don't get twisted on the formula. Suppose that we have a collection of 5 books, a set of 5 books, and then we want to choose 3 of them to take with us on the, on the holidays to, hopefully read them. But the thing is that for a problem like this, because you have like ordering, arrangement, and repetition, right? We have both of these in here, but this is fundamentally different. The formula is the same. We're choosing our books, 3 books out of 5, which would give us n factorial. Fuck. So we have a set of 3 books and then 2 other books that we're not choosing, right? Now, same strategy. For the denominator, we calculate the entire thing, the entire branch, treat them as, all the possibilities, right? We have 5 factorials, but now we have a bloated number, right, in n factorial, because we counted the stuff, we counted the permutations in here. So these guys, whatever you put in here, as you permutate them, they don't matter. It becomes 3 factorial. But the thing is, you have 2 other fuckers in here. In this 5 factorial, not only have we counted these guys as separate entries in our possible outcome tree, but we have also counted these 2 guys, right? Out of 5, we chose 3 to put in here, and then discounted permutations from 5 factorial, and then right now we only have 2 more options, so we get 2 factorial, right? Because it doesn't matter whether let's say we choose A, B, let's say we have A, B, C, D, E, right? If we choose this exact set, right, A, B, C, it doesn't matter whether we leave out D and E, or we leave out E and D. But 5 factorial counts these guys as separate entities, right? So that's why we have division by 2 factorial. But exact same formula, different concepts. It's a different logic with exact same abstraction, which gets us the same formula. That's why you don't memorize fucking formulas. You follow the logic. Okay, back to the main problem. We have all the different sequences possible to get 3 heads and 4 tails with this, right? That becomes our thing. But be careful, conceptually, they're different. We have permutations within 2 sets that we're kind of de-bloating 7 factorials with this concept, not this concept. Okay? I don't know if I'm making sense, but yeah, we're doing the thing. So if we generalize this for anything, right? Any sets, we have this guy. This becomes our formula times probability of the thing, okay? What do you call it? Probability of 1 powered by it says, okay? It is R times probability of 0 n minus R. Okay? So that's it. Yeah. This is where the fucker comes from.